In modern computing, we often see a tension between the flexibility of general-purpose CPUs and the raw deterministic efficiency of ASICs. While consumer tech relies on the broad utility of the von Neumann architecture, many high-performance applications, from signal processing to hardware acceleration, demand the parallelism of dedicated silicon. This project explores the middle ground, the FPGA. Specifically, I'm working with the Xilinx Zing 7000, a system-on-chip that integrates a dual-core ARM processor with a programmable logic fabric. My objective was to implement a hardware-level control system for the board's onboard peripherals managed through a high-level web interface. This demonstrates the seamless bridge between software-defined commands and hardware-defined execution. In the following walkthrough, I would document the implementation within Xilinx Vivado, focusing on the hardware configuration and the synthesis of the bit stream required to initialize the logic gates. I begin by initializing a new RTO project in Vivado. Naming the project establishes the directory for our hardware description and bitstream files. Selecting the PIN-QZ2 board is critical. It maps the physical pin constraints for the Q 7000 SoC. With the project confirmed, the workspace is ready for hardware-software co-design. To bridge the web interface in the hardware, creating a custom IP peripheral. Using the AXI4 Lite interface allows the ARM processor to talk directly to the hardware registers controlling the LEDs. I access the HDF sources to define hardware ports. I declare a 4-bit output for the physical LEDs. I instantiate the AXI interface to bridge our logic with the processor bus. The LED signal is mapped to internal slave registers. I assign SLV register 0 bits directly to the LED output. This enables software commands to trigger hardware states. I return to the IP packager to update file groups. I merge all changes to synchronize the hardware-software interface. Moving into the IP integrator, initialize a new block design to visually assemble our system components. First, I add the custom peripheral which is packaged, which contains our LED control logic. Next, I instantiate the Zing processing system. To streamline the setup, I trigger block automation, which applies to PIN-Z2's preset hardware configurations. Consequently, I use connection automation to automatically route the AXI interconnects between the CPU and our IP. By doing so, the software to hardware communication bus is electronically mapped and validated. I select Make External so that our internal 4-bit signal can physically reach the board's onboard LEDs. Finally, I run design validation to confirm that our time constraints and bus protocols are error-free. With the block design validated, I next generate an HDL wrapper to translate our visual diagram into a top-level Verilog file. This allows us to initiate the synthesis process, where Vivado converts the RTL description into a gate-level netlist. By launching this run on a local host, the software begins the intensive task of mapping our logic to the specific sizes of the Zing chip. Once synthesis is complete, I open the synthesized design to perform the critical step of physical pin assignment. Opening the schematic view provides a low-level visualization of the hardware, gates, and I/O ports generated. Furthermore, this view is essential for accessing the I/O ports table, where we must manually define the physical board locations for our signals. Consequently, I consult the PIN-Z2 user manual to identify the exact package pins, such as R14 and P14, connected to the onboard LEDs. I then map our let-out signals to these specific package pins within Vivado, ensuring this FPGA logic reaches the correct hardware components. Finally, I save these configurations into a new physical constraints file, or XDC, which freezes our pin mapping for the final implementation. I initiate bitstream generation to produce the binary configuration file. This process translates our logical design into a physical gate level map. Next, I open the hardware manager to connect to the PIN-Z2 via JTAG. I then select Program Device to prepare the SoC for configuration. By downloading the bitstream, the FPGA fabric is reconfigured in real time. I launched a Node.js server to bridge our web interface with the hardware. Finally, toggling the UI triggers immediate, deterministic responses from the LEDs, which is pretty cool.